Welcome back to Chem 4300. In this video, we're going to begin Chapter 16 on the quantum particle moving in 3 dimensions. Now, so far, we've only looked at the quantum mechanics of motion in 1 dimension. And generally speaking, there are some significant changes in the physics of the problem when you allow motion in 2 and 3 dimensions. For example, in the physics of rotational motion, we saw that we had to introduce the angular momentum vector, which we also saw was an important quantity for describing the rotational motion of rigid bodies. Now, in classical wave motion, we saw that a significant change occurred when we went from 1D to 2D and 3D, where the wave number became a wave vector. And that wave vector specifies not only the wavelength of the wave, but also the direction in which that wave is propagating through space in 2 and 3 dimensions. Now, of course, you know that that wave vector for a quantum matter wave is related to a particle's momentum vector through the constant of h bar. So let's take a look at some of the new concepts and consequences of quantum mechanical motion in 2 and 3 dimensions. Now, one thing that we have to worry about is how the linear momentum operator is going to appear in 3 dimensions. And we've already worked out the momentum operator for 1 dimension applied to the wave function in the position basis. And we saw that that was just minus IH bar, the derivative with respect to x. So now in 3D, it's going to be the partial derivative with respect to x. And additionally, we're going to have Py and Pz, which have their corresponding partial with respect to y and partial with respect to z. Now, the momentum operator is now a momentum vector operator. And so we need to take all of those components and multiply them times the unit vectors along the directions x, y, and z. And when you do that, then the momentum vector operator becomes minus IH bar times the gradient operator. Similarly, the kinetic energy operator, which is from classical physics, just px squared over 2m plus py squared over 2m plus pz squared over 2m. We know we just put hats on these guys, and then we can take these definitions here and substitute them in over here, and we get that the kinetic energy operator has this form, and we recognize this term in parentheses here as just the Laplacian. So the kinetic energy operator is just minus h bar squared over 2m times the Laplacian operator. And now we made the transformation of momentum and kinetic energy from 1D into 3D. And the main difference is that we have to use the partials now, and this guy's a vector quantity. Okay. Now, let's go to, say, a free particle moving in three dimensions. So the Schrodinger equation is going to be h psi equals E psi. And for a free particle, which, say, has moving in a constant potential, which we'll say is 0, then we can write down the Schrodinger equation here. And the solution for this, the eigenstates for this differential equation, will be this stationary state that we see here. Now, for a free particle, which has a momentum of h bar k, then we can take the plane wave solution to this differential equation, and we can identify then that the k dot r just becomes p dot r divided by h bar, and then we have the, using omega from E equals h bar omega, we can make this substitution over here, and we see that how these guys, that the stationary state, the psi of r is just going to be related to the momentum there. Okay, so that's it for the free particle. What I'm really interested in is looking at now the particle that's in an infinite 3D well. So we've looked at the particle in a box. Now we're going to look at the particle in the 3D box. So let's take a look at the potential that we're going to use. It's this form here. So it's very similar to what you have in the 1D case, just generalized for 3D. So the potential is going to be equal to 0 when x is between 0 and Lx, y is between 0 and Ly, and z is between 0 and Lz. And outside that box, the potential is infinite. Now, when we solve the Schrodinger equation, we're going to assume that we can write the wave function with the separation of variables. So we're going to write x of x, y of y, and z of z as our product of 3 wave functions. And again, this is a guess. We'll put it into the Schrodinger equation. If we get valid solutions, then we had a good guess, right? So we'll plug it into the Schrodinger equation. the time-independent Schrodinger equation, and we'll get this expression here, which looks a little messy here, but what we're going to do is we're going to rearrange this by dividing by the wave function and trying to get rid of some of these constants here. So let's do that in the next slide. So I divide by the wave function, rearrange it. I can put it in this form where I've defined k squared as 2me over h bar squared. And this gives me this partial differential equation. So now we have to solve this. And we know a few tricks now at this point in the course. So we know, for example, that we can rearrange this. We put everything with respect to x on the left and everything that doesn't depend on x on the right. So this allows us to define a separation constant, which I'm going to call minus kx squared for reasons that will become obvious soon here. And that will give us an ordinary differential equation for x that has this form, and we've now decoupled one of our variables in our partial differential equation. So let's move on and see that we can take our what's left over here and we can rearrange that into this form where now we have everything that relates to y on the left, everything that doesn't relate to y on the right, and we can define another separation constant, this time minus ky squared, and that gives us an ordinary differential equation for y. And then finally, what we have left over with z is this. So I'm going to define a new separation constant, which I'm going to call kz. So where k squared is equal to kx squared plus ky squared plus kz squared. With that definition, this here becomes this equation, and now we've separated all of the variables. We have ordinary differential equations for the three different variables. So here's what we have to solve in this particle in an infinite 3D well. Now, each one of these is exactly the same as as the particle in the 1D well, so we know the solutions, they're sinusoids, and we know the boundary conditions, how that's going to affect the values of kx, ky, and kz. And so here's the result. So we get, solving each one of these, we get these solutions for our wave functions. The kx, ky, and kz, because of the boundary conditions of the box, can only have values of n pi over L, where these, for the kx, it's nx pi over Lx. For ky, it's ny pi over Ly, and kz, it's nz pi over Lz, where nx can be 1, 2, and 3, ny can be 1, 2, and 3, and so on, nz, 1, 2, and 3, and so on. And so all of these integer values, these are the quantum numbers for the particle in an infinite three-dimensional well. Now, if I calculate the total energy, which we can find will be h bar squared over 2m times kx squared plus ky squared plus kz squared, and then substituting in these definitions here, we get an expression which should look familiar if you remember from the 1D particle in a 1D well. It just looked like this part right here, but now if it was just 2D, we would just have that extra term, and now with 3D, we have these three terms here. So we've solved the particle in an infinite 3D well. Not so bad, a very simple generalization of what we learned in the 1D case. But now the most important difference is that we have three quantum numbers associated, one for each direction or dimension, nx, ny, and nz. Now this introduces some interesting things with the energy. So one of the things we'll notice, say, in this case, let's say we take a box that is a cube. So we're going to take Lx equals Ly equals Lz is equal to just one length. So in that case, the energy expression has this simpler form, and this form allows the possibility for what we call degenerate energy states. So whenever different states with different values of nx, ny, and nz lead to exactly the same energy, we say that those states are what are called degenerate states. So a particle in a 3D box will have degenerate or identical states, and this is not something that we would see in 1D. So it's only when we get to 2D and 3D that this type of behavior of degenerate states shows up in our particle in an infinite well. So for example, if I have nx equals 2 and y equals 1 and z equals 1, that will give me this energy. But similarly, nx equals 1 and y equals 2 and z equals 1 will give me the exact same energy, and also nx equals 1 and y equals 1 and z equals 2 will give me that energy. So this is a set with nx and y and z that has a threefold degeneracy. Three different sets of nx and y and z give me the exact same energy. Okay. These type of degeneracies will play a very important role when you get to the application of statistical mechanics to quantum mechanical systems. All right. So if I took a look, for example, of the particle in the 1D box, and I plotted a histogram of the number of states that had a given energy, well, in a particle in a 1D box, all the states have no degeneracy. So there's only one state for each n value. So if I plotted those histograms, then there'd only be a bin going up to a height of 1 for each one of those states. And for those n values, n equals 1, 2, 3, 4, you can see that the energy gap, the gap between those n's, is getting bigger and bigger. All right? Now, in 2D, if we did the same thing, then we would have an energy that is going to be, well, energy scaled by this set of constants here is going to be nx squared plus ny squared. And now we have the possibility of degeneracies in this square box where Lx is equal to Ly. And you can see that you have, okay, again, nx equals 1 and y equals 1, it's singly degenerate. There's no degeneracy here. But for nx equals 1 and y equals 2, or ny equals 2 and x equals 1, then we have a twofold degeneracy. And you can kind of work through all of these, if you like, and try to figure out ways in which you can get, here you can get a fourfold degeneracy, here's a threefold degeneracy, all with this equation here. Now, in 3D, we have now an energy which is scaled by this constant, which looks like nx squared plus ny squared plus nz squared, and you can see that we get quite a bit of degeneracy. In fact, when you look at these plots, you can see that there's sort of an interesting behavior. There's no degeneracy here for any of the states, and you can see that the degeneracy, that the energy levels seem to be be lower and lower density as we get to higher and higher n values. Whereas here we look at the density of the states, and we find that it's about the same as we increase the energy. But here you see in 3D that the density of these states, of these degenerate states, starts to get higher and higher as we go to higher energies. And that's, again, another important distinction between 1, 2, and 3D. So in other words, this, what we call the degeneracy of the states, the number of states in a given window of energy, is going to decrease as we increase energy in the 1D case. So here, if I look at a window, I might have some, I can see in this window I have 3 states. I move over, now I have only 2 states. The same window, only 1 state. And soon over here, I only have 0 states in the same window. So it's decreasing as we increase the energy. In the case of 2D, the density of states remains roughly constant with increasing energy. So if I look at a given window here, I find that there's, in this case, there's a certain number of states. It's about 1, 2, 3, 4, 5, 6. I move over 1, 2, 3, 4, 5, 6, 7. Here it's about 7, and you can see as I move over, it's about, it varies a little bit, but it's about the same as I move back and forth on this. But then you see here that in the 3D case, as I go across with the same window, well, obviously it's getting bigger and bigger, the number of states in the same in this fixed window as I move to the right, because so what we say is the density of states is increasing. So what I'd like to do is try to find an expression that sort of models this increase in the density of states. So in the 1D infinite well, we know that the energy is given by this expression here. And I'm going to rearrange this so that I can take the derivative of this with respect to the energy, because the number of states in a given energy level, that's my density of states. So if I take this expression and I rearrange it, then I take the derivative with respect to the energy, then I'll have the number of, the sort of number of states per given energy width. And that comes out to be this expression here. So taking the derivative of this with respect to E, and you can check this, you get this expression here. And what we find is that we have these constants out here and L, but then we find mainly that the density of states goes as 1 over the square root of the energy. So as the energy increases, the density of states is decreasing as 1 over the square root of the energy. And that seems consistent with what we saw in those plots. As we went further and further out, the number of states in a fixed window would become less and less, and it's decreasing with 1 over the square root of E. If we go to the 2D case, well, here it gets a little bit trickier to do this derivation, but stay with me. We're gonna take nx squared plus ny squared, and we're just going to define a new variable just called n squared. And n squared is equal to this. And so n is equal to the square root of nx squared plus ny squared, and that's equal to this energy here. Now, what I'm interested in is the number of ways in which I can get a fixed energy. So that means that since n is equal to this expression here, I'm looking for the number of ways in which nx squared plus ny squared square root will give me the same value of n. Well, if you look at this, this is really the equation of a circle, right? N squared is equal to nx squared plus ny squared. So if you remember your geometry, that's the equation for a circle. And since nx and ny can only have positive values, then we're really looking at the positive quadrant of that circle. So even though the circle goes all the way around, we only allow ny and nx values to be positive. So what we're saying then is that all of the values of n, where nx squared plus ny squared is equal to the same value, are all along the line here, the curve here, which is this circle. So if I take the circumference of the circle just in this quadrant, so just this quarter of the circumference of the circle, and I multiply it by some width dn, then I'll have the number of states that are in that along this curve with this width dn. So I'm going to take 1/4 of the circle circumference, if you remember that, is 2 pi r. Well, r is equal to n now. And I'm going to multiply that times some width dn, and that's going to give me the number of states that are in that region, which coincide to the amount, the density of states there. So in other words, we're going to say that the density of states is 1/4 times the circumference times dn, that's the width, and then divided by some fixed energy difference. So what we're going to do is rearrange this, and that just becomes 2 pi n over 4 dn de. We have our expression for n as a function of e, so we take the derivative of this. I'll rearrange this a bit and take the derivative of that, and we get this expression here. And then we see that there is no energy dependence in the density of states. So there's no E here. If you remember in the previous slide, it went as 1 over the square root of E for the 1D box. But in the 2D box, there's no dependence on E, which means that the density of states should be independent of the energy. And that's what we found, right? In 2D, there was no dependence on the energy. So if we go back real quick, then we saw that here the density of states is decreasing with 1 over the square root of the energy. Here the density of states seems to not matter, seems to be independent of the energy. So now we move to 3D. So I'm not going to draw the picture in 3D, but it's going to be very similar. Instead of a quarter circle, imagine that we're going to have a sphere that's described, the surface of a sphere that's described by nx squared plus ny squared plus nz squared square root is equal to n. Again, very similar arguments there. And now we're going to take only 1/8 of the surface area of this sphere, 1/8, because that's the quadrant where nx, ny, and nz are only allowed to be positive. And so the surface of the sphere is 4 pi r squared. Take 1/8 of that, multiply it times dn for some thickness, and that's the number of states that lie in n to n plus dn. That gives us this equation here. So 1/8 of the surface area of the sphere times some thickness dn divided by this energy width, and that gives us this equation here, and we have the expression for n with respect to E, so we take the derivative of that, dn dE of this, and that gives us this equation here. The density of states is equal to these constants times L cubed times the square root of the energy. So here the density of states will increase with increasing energy, and it increases by the square root of the energy. So again, consistent with what we saw in that histogram. So I'm going to go back here real quick and just kind of summarize here, is that here we see a decrease with increasing energy. It decreases as the square root of the energy. Here it's independent of energy, and here it increases with the square root of the energy. So that's it for this section, and we will continue to look at the consequences of moving from 1D to 3D. We just saw that degeneracy is an important concept. The next concept we're going to look at is the concept of angular momentum in quantum mechanics when we're moving in 2 and 3D.